Welcome guys. In this video, we're asked to solve this very problem. My name is DrAvitech and we're going to start solving them. But before then, remember to hit the subscribe button, like this video and share it across to your classmates. Now the first thing you want to know is Fourier series is all about representing functions in terms of sines and cosine. So we'll try to see in every function, is there sine in that function? Is there cosine embedded in it? It's like a gene. It's a better way to say it, that this is like a gene, an encoding inside the function that we need to see if this minus x, or if this graph has sine x embedded in it, has cosine x embedded in it, or has the both of them together, because they can be together. Now, the first thing we want to do is to analyze the function. But the good thing is this problem, they've already analyzed it for us. So they told us that the function is minus x from minus pi to 0. From minus pi to 0, this is the line. This line you see here is minus x. That's what I'm trying to say. And then from 0 to pi, it was 0. So from 0 to pi, it was just 0. It was flat all through. It was 0. That's what I'm trying to say, that from 0 to pi is just 0. So it's actually a good one. And I kind of like the problem. Now this next part, f of s plus 2 pi equal f of x, what it's trying to tell us is, for every 2 pi you add to the function, you would always get the function back. So it means that the period of the function is 2 pi. Now, if the period of the function is 2 pi, there are easy ways to just evaluate your, your values. So the first one is a naught. A naught is 1 over pi integral from, since the function is from minus pi to pi, you're going to write minus pi to pi of f of x dx. But remember that this integral part is just asking us about the area of the function. That's what it's just asking us. And since we can easily find the area, I don't really think we should be stressing ourselves. Yeah, we can easily find the area. So let's just find it. So this is 1 over pi times, this shape is a, it's a triangle. So that's half base times height. So this is 1 over area times half. The base, which is the bottom here, is pi. Please take note, this is like 0, from saying 0 to pi. You won't put minus pi, please, because the areas above this y part is positive, then the areas below is negative. So this guy is positive, while this guy is negative. Take note. So because every single part of the diagram is upwards, the value of s will stay positive. It is the y that determines if it's negative. So if it's above this 0 line, it's going to be positive, but below it's going to be negative. So that's what we conventionally just do. So that's pi times, what is the height? What is the height of this diagram? The height, how high it is from this point to this point, is pi. Okay, so pi we cancel at pi. So that means we're going to be having pi over 2. Is that it? Yeah. I think that's it. So we're going to be having pi over 2. So that's a naught. A naught is what? Pi over 2. Don't worry, you can actually confirm it using the integral. I don't think I have the strength to do that. But remember, please, remember that if you are not convenient with using the area part the way I'm using the area, you can just go ahead and use your integration. It will still be the same. It will still be the same, just to save time. And I do this if I can find it. If my shape is a triangle or a rectangle or a square, I know I can find the area, so I make use of this. So that's me. But you can actually still practice and understand how this is going. The next one is a sub n. So a sub n is 1 over pi, integral from minus pi to pi of f of x cos nx dx. So this is what we have. This is what we have. All right. Okay. So this is 1 over pi. Now, our function, this function you see right here, there's no function value that started from minus pi to pi. There was no function value that started from what? Minus pi to pi. Also, just before I forget, if you notice, I didn't take note of the 0 part, because this 0 line, I only used this triangle here. This 0 line did not form any shape. So the area at this point should just be 0. So that's why I did not use it. So here you will notice that I will still do the same thing, but I just want to explain it. So in future examples, you understand why I threw it away. Now, there was no single function value that ran from minus pi to pi. None. Instead, there was a break on the way. There was minus pi to 0 first before 0 to pi. So our integral has to change for integral from minus pi to 0 of f of s cos nx dx plus integral from 0 to pi of f of x sin nx dx. So that's just the difference. That's just the difference. But it's still the same. Okay, so this will be 1 over pi, then integral from minus pi to 0, then f of x. What is f of x from minus pi to 0? F of x was minus x. So this is minus s cos nx dx plus integral from 0 to pi. What was f of x from 0 to pi? From 0 to pi, f of s was 0. So zeros. Hold on, did I write sign here? No. I must be on drugs. This is supposed to be cosine because I'm dealing with a sub n. So this is cosine of nx dx. All right. Now this will be 1 over pi. You do agree with me that this very portion you see here, everything here will just be 0 because 0 times cosine is 0. Integral of 0 is 0. That was why this part will go away. Same reason I didn't do it. Same reason I didn't take it into cognizance when finding area, because the 0 would turn everything to 0. So let's come back here. Now this minus here can come outside. Since this is the only integral remaining, the minus can come outside. Then we have the integral from minus pi to pi of s cos nx dx. So what we do next is to integrate using integration by parts. But the thing is, it's a shorter way to do that. So this will be minus 1 over pi. I'm going to write x. Now this very x that I've written, I'm going to start differentiating x. So differentiate x, what would you get? You're going to have s, sorry. Differentiate s, you're going to have 1. Then differentiate 1, you're going to get 0. But there's no need for the 0 because 0 is nothing. So throw that 1 away. And this is cos nx. Integrate cos nx. So let's integrate the cosine first. Integrate cosine, you get sine nx. Then differentiate the nx. You're going to get n. Now this is sine nx over n. We're going to now integrate this again for this part. So times integrate sine, we're going to have minus cos. Then you put your nx over, differentiate the angle nx, you will get n. Now the n will come and times this n that is here to make this n squared. Now sometimes, if this is difficult, you can still go through your integration by parts. But with time, you have to learn this. You have to learn this because life will be much more easier if you understand this. So then you put a plus, you put a minus here. Close this up and put your limit. Oh, this is minus pi to 0. Minus pi to 0. So this is minus pi down to 0. Okay, now let's simplify this bracket. So this will be minus 1 over pi. And then we're going to have x sine nx over n. Minus times minus is plus cos n squared over, cos nx over n squared from minus pi to 0. Now here's the thing. Sine nx is a very funny function. When you put in 0 here, sine 0 is 0. So this will be 0. When you put in minus pi here, sine of n times minus pi or sine of minus n pi is still 0. So sine n pi is equal to 0. Sine of minus n pi is equal to 0. Sine of 0 is equal to 0. So what this tells me is this guy will just be eliminated. It's gone. It's gone. So only this guy will be useful. So this is minus 1 over n. Minus 1 over pi. And then this is cos nx. So let me put in my 0. So this will be cos 0 over n squared minus cosine of minus n pi over n squared. Good. Now remember that the n squared, this n squared you see here, is actually a constant, so you can bring it out. So So this is minus 1 over n squared. Should I say pi n squared? Yeah, pi n squared or n squared pi, any of them. I would have just brought it out here. I would have just brought it out here. Yeah, so, but it's still the same. It's still the same with when I bring it out here. We're factorizing. So since n squared is here, means n squared is common. So you can factorize it out. Then what will be left to then become the cos 0 minus cos of n pi. Now if you notice, the minus here disappeared. Why did the minus disappear? Because cosine is a function that if the angle is negative, it doesn't affect the value. It has the same value when it is positive. What I'm trying to say is cosine is an even function. So even if you put a minus with the angle, the answer will still be the same when it's positive. So that is why the minus n pi is the same thing as n pi. It's still the same thing. So this is minus 1 over pi n squared. And then cos 0 is a special angle, that's 1. Minus cos n pi is minus 1 to the power of n. These are special values that don't change. Cos 0 is 1. Cos of n pi is minus 1 to the power of n. Now, I would have actually left my value like this. I would have left this and said this is a sub n. But do you know that for some reason, I can actually still simplify this further. The reason is this. If I look at the brackets, these brackets can be 0 sometimes. The brackets can be 0 sometimes. The brackets can give me 2 sometimes. How do I know this? This n here, because when you're evaluating your Fourier series, n is going to be a number starting from 1 to infinity because you're summing from 1 to infinity. Fourier series is an infinite sum. So from 1 to infinity. So the n right here is going to be a sum. There's going to be a time when you start putting numbers. So since this is going to be a sum, dealing with the bracket alone, this is a constant. So I'm going to keep this one the way it is. The n here will not be affected. So I'm going to keep this one the way it is because this bracket tells me how this would be. This bracket is just like a multiple. Just like a multiple of this. So I'm just going to deal with this bracket alone. So looking at this bracket, I know that sometimes this will be 0. So let us say when n is odd. When n is an odd number, because when we are dealing with numbers, we have either odd or even numbers. So when n is odd, so when n is, let me say 1, for example. 1 minus 1 to the power of n would then become 1 minus 1. Let's say to the power of 1. Because even if you say to the power of 3, to the power of 5, to the power of 7, your answer will still be the same because you are picking odd numbers. So this is 1 minus, what is minus 1 to the power of 1? Anything to the power of 1 is that same thing, minus 1. So this will give me 1 plus 1, so that's 2. You see that, right? So as you can see, this is now much more easy because this expression looks bulky. If I want to evaluate the Fourier series using this bulky expression, I have to start dealing with this over and over and over again. Meanwhile, life could be better because when I get to when the numbers are odd, I'll just put in 2. So it's just going to be 2 times this. Since the odd values will remain the same, these 2 will remain constant as long as n is odd. So that's for this one. But let's see, when n is even, everything will be 0. Everything will be 0. So when n is odd, let's simplify our a sub n. So a sub n would then become minus 1 over n pi. Okay, wait. I don't know if I should put the n or the pi squared first. Okay, n squared pi times, the bracket was 2. So this will be minus 2 over n squared pi. Now this is when n is what? Odd. This is when n is odd. The reason I did this is because it will be much more easier if I do it like this, to save myself some time in the future. That's why I'm doing this. Now let's also see what will happen if n is even. So when n is even, so the bracket 1 minus 1 to the power of n, this will be 1 minus 1. N is even, so let's pick 2 as an example. So this will be 1 minus 1 squared. If you square a negative whole number, you get 1, or you will get a positive of it. So this will be minus 1 squared is 1. 1 minus 1 is 0. So as you can see, a sub n will then become minus 1 over n squared pi times this whole bracket here is now 0. So it means a sub n is 0 when n is even. So you see, when I'm evaluating my Fourier series, instead of stressing myself to be putting even components for a sub n, I won't be putting the even component because it's 0. So I'll just skip that. So that is why it's better you kind of get all of this. I think I should write this thing somewhere. Kind of like writing my answer so that I'm going to wipe the board so I wouldn't forget what it is. So a naught is pi over 2. A sub n is minus 2 over n squared pi. That's a sub n. So let's find b sub n. Now to find b sub n, the formula will be b sub n equal 1 over pi integral from minus pi to pi of f of x sine nx dx. So what this does for us is it tells us how much of sine we have embedded in the function. So this will be 1 over pi. Now remember that we're going to break our integral down. We're breaking our integral because there are two different intervals. There's minus pi to pi and there's 0 to 2 to pi. So let's start from minus pi to pi. So we have minus pi to pi. The function was minus x at that point. So this is minus x sine nx dx. Now I would have said plus the integral from 0 to pi. But the thing is, the function was 0 at that point. So the integral would just be 0. So no need for me to write it. If you notice from the previous example, there was no need for me to write it. So that guy is gone. No need. Let's just, this should be to 0. Why do I keep putting this thing there? When it was minus x, it was from minus pi to 0. So this was supposed to be minus pi to 0. I think it's because I'm too close to the board. I should be writing from a far distance. But it's still the same. So take this minus outside. So this will be minus 1 over pi. Integral from minus pi to 0. X sine nx dx. Okay. Now we're going to use integration by parts here. So this is minus 1 over pi. Now, instead of me using the normal uv minus integral of u dv equal to integral of v du. Instead of me using this, I can just make use of something better. So let me write x. This is a shorter way. Let me write x. So this x that you have seen here, I'm going to differentiate x. So differentiate x, you're going to have 1. Now differentiate this one, you're going to have 0, but there's no need for that 0. So that one is gone. Now the next thing I'm going to do is, this is sine nx. I'm going to integrate sine nx. So integrate sine nx, you'll be getting minus cos nx over, differentiate the angle, you will get n. Close this bracket up. Now this very angle you see here, you're going to integrate this again. Integrate this whole expression again here. So this is times, put the minus, integrate cos, you would have what? Sine. Then put your angle nx over, now differentiate this angle ns, you will get n. But since you are dealing with this whole expression, there was an over n before. So if the two n's meet together, that would be n squared. Now this is plus minus. No, this is plus minus. So I'm just following the formula. And then I'm going to put my limit minus pi to 0. So let's simplify the bracket. So this will be minus 1 over pi. I can break out the minus. So this is minus x cos nx over n. Minus times minus is plus sine nx over n squared. And then minus pi to 0. That's what I have. Now, remember that if we're dealing with this, if we're dealing with minus pi to 0, and you have a sign, every single thing will just be 0. So I don't really want to stress myself because every single thing here will be 0. So when I put in 0, it will still be 0. So just take that guy out. Let's deal with this very one. So to deal with this very one, to deal with this very guy, the minus here is a constant. The over n is also a constant. So bring out this minus, bring out the over n. So this will be minus minus is plus. So this will be 1 over pi times n will give me my n pi. The one will be remaining will become s cos nx from minus pi to 0. That's what I have. So this is minus 1 over n pi. And then this x here, for the first one, for the upper limit, x will be 0. So this will be 0 cos 0 minus x. The second time will be, wait, why did I put a minus here? Sorry. So the second time, s will be minus pi. So this will be minus pi cosine of minus n pi. Okay. Now this is 1 over n pi. 0 cos 0, everything here will just be 0 because 0 times cosine is 0. Minus times minus is plus. So this will be pi cos minus n pi is the same thing as just having n pi. Now pi will cancel out pi here. So this is 1 over n. This value you see here, cos n pi, is minus 1 to the power of n. It's minus 1 to the power of n. So you could just write this as minus 1 to the power of n all over n, if you wish. Now this very value you see here really makes no difference if it is, what's it called? If it is odd or even. Just that, if it is odd, you know it will be minus 1. If it is even, you know it's just going to be plus 1. Just like, okay, I've wiped that part out. Just like we've done before. Minus 1 to the power of n is going to be positive if n is 2. Because minus 1 squared is positive. Then it's going to be negative if it is odd. So it's not really a big of a deal. So it's not a must that you write that one. So b sub n is minus 1 to the power of n over n. Now, after finding all of the coefficients, it is time to now write the Fourier series of the function. So the Fourier series formula for this will be f of x equal a naught over 2 plus the sum from n equal to 1 to infinity of a sub n cos nx plus the sum from n equal to 1 to infinity of b sub n sin nx. Now a naught was pi over 2. So if you have a naught as pi over 2 and you are dividing it by 2 again, that means you're going to be having pi over 4. That's the meaning. You're going to be having pi over 4 plus the sum from n equal to 1 to infinity. A sub n is minus 2 over this. So this is minus 2 over n squared pi. But there's a problem. Remember that this was when n is odd. So always remember. So sometimes you can just put at the bottom, comma, odd, if there's space. Because it's very important. You shouldn't go and put an even value there. Because when it's even, it was 0. Remember that we solved for this. When it's even, it's going to be 0. And then this is cos nx plus the sum from n equal to 1 to infinity. B sub n, this one is all weather. So whether it's even or odd, this is just it. Minus 1 to the power of n over n sin nx. So now let's see if we can factorize. Yeah, I can actually factorize here. So this is pi over 4 plus, let me not put plus, because the minus 2 is a constant. So if minus 2 come outside, it will affect this plus. So this pi is also a constant. So I'll bring out minus 2 over pi. This is minus 2 over pi. Then the sum from n equal to 1, where n is odd, to infinity, of what will be left will now become 1 over n squared. Because after the minus 2 is going to be a 1 at the top, then n squared will be remaining. Cosine of nx. And there's no constant here. So this will just remain the same. N equal to 1 to infinity of minus 1 to the power of n over n sin nx. Okay. Now, this expression, you could actually say that, okay, this whole thing here is how your function would be in terms of n. But there's a problem. If your question actually says leave your answer in terms of n, this would be an issue because n equal to 1, comma, odd. You can't really specify, you can't really tell your graphic calculator, comma, odd. Your graphic calculator will not understand. But there's a way to write this function in such a way that every single thing you put in for n will become odd. Here's what I'm trying to say. If you replace all the n with 2n minus 1, all your values will be odd. All values will be odd. Let's try it. Let's try it. When n is 1, if you should put 1 here, 2 times 1, 2. 2 minus 1 is 1. 1 is odd, right? The next value for n, 2. Let's put in 2. 2 times 2 is what? 4. 4 minus 1 is what? 3. That's the next odd number. Now, the next n is going to be 3. So, 2 times 3 is what? 6. 6 minus 1 is what? 5. So, you can see that, right? Beautiful. So, let us turn every single thing here. So, this will become pi over 4 minus 2 over pi. Then I'll sum. This n here will still be n equal to 1. So, start from n equal to 1 to infinity. Then 1 over, we want every single n here to be odd. So, no need for us to be writing this odd guy. So, this will become 2n minus 1 squared cosine of 2n minus 1x, and then plus this one should just be the same. The sum from n equal to 1 to infinity of minus 1 to the power of n over n sine nx. Please take note, I only did this for persons or students who their exam might say leave your answer in terms of n, and they are having something that deals with odd here. This is what you do. You say n should become 2n minus 1. Okay, so that's what we have. Now, let us write some terms inside the Fourier series. Let us write some terms inside the Fourier series. Because all of these are all expressions for f of x. Let us write some terms. This n here, let us put in some numbers. So this will be pi over 4 minus 2 over pi. Open up a bracket. Let's put in some numbers. But I don't want to use this one. This one is looking kind of complex. Let me use this one. So when n is 1, 1 over 1 is still 1. Then cos 1x is just cos x. So this is cos x plus, what will be the next one? 3. You won't put 2 because this has to be odd. So put in 3. So 1 over 3 squared, that's 1 over 9. So this is 1 over 9 cos n is 3. So this is 3x. Next one will be what? 1 over 5. So 5 squared. 5 squared is 25. Then this is cos 5x. So as you can see, here n was 1, n here was 3, n here was 5. So we're picking just the odd ones. So this will continue just like that. And then close the bracket. Then for this other one, plus. Now when n is 1, remember, if this is odd, this will be minus 1. So this is going to be bracket minus 1 sine x. Then plus 2. When it's 2, it's going to be even. That's why I wrote plus. So this will be 1 over 2 sine 2x. Next one is 3. So when it's 3, minus 1 to the power of 3 is minus 1. So this is minus 1 over 3 sine 3x. And you can now get the pattern, right? Plus 1 over 4 sine 4x minus 1 over 5 sine 5x plus 1 over 6 sine 6x, just like that. You can't really write to infinity, so you must stop somewhere. So this would be the complete Fourier series expansion for it. So with this, I believe I've been able to convince you and not to confuse you that Fourier series is actually easy to evaluate. So this will be all for this very video. I'll see you in the next one. Bye.